The Chern-Simons theory, named after Xiang-Shen Chern and James Harris Simons, is a three-dimensional topological quantum field theory of Schwarz type, developed by Edward Witten. It is so named because its action is proportional to the integral of the Chern-Simons 3 form. In condensed matter physics, Chern-Simons theory describes the topological order in fractional quantum Hall effect states. In mathematics, it has been used to calculate knot invariants and three-manifold invariants such as the Jones polynomial. Particularly, Chern-Simons theory is specified by a choice of simple Lie group G known as the gauge group of the theory, and also a number referred to as the level of the theory, which is a constant that multiplies the action. The action is gauge-dependent. However, the partition function of the quantum theory is well defined when the level is an integer and the gauge field strength vanishes on all boundaries of the three-dimensional spacetime. The classical theory, mathematical origin in the 1940s. S. Chern and A. Weil studied the global curvature properties of smooth manifolds M as der RHAM cohomology, which is an important step in the theory of characteristic classes in differential geometry. Given a flat G-principal bundle P on M, there exists a unique homomorphism, called Turnbull Homomorphism, from the algebra of G adjoint invariant polynomial on G to the cohomology. If the invariant polynomial is homogeneous, one can write down concretely any k-form of the closed connection omega as some 2k form of the associated curvature form omega of omega. In 1974 S. Chern and J. H. Simons had concretely constructed a form df such that, where T is the Turnbull homomorphism, this form is called Chern-Simons form. If df is closed, one can integrate the above formula, where C is a dimensional cycle on M. This invariant is called Chern-Simons invariant, as pointed out in the introduction of the Chern-Simons paper. The Chern-Simons invariant CS is the boundary term that cannot be determined by any pure combinatorial formulation. It also can be defined as, where is the first Pontryagin number and S is the section of the normal orthogonal bundle P. Moreover, the Chern-Simons term is described as the eta invariant defined by Atiyah, Patodi and Singer. The gauge invariants and the metric invariants can be viewed as the invariants under the adjoint Lie group action in the Chern-Weil theory. The action integral of the fields theory in physics is viewed as the Lagrangian integral of the Chern-Simons form and Wilson loop holonomy of vector bundle on M. These explain why the Chern-Simons theory is closely related to topological field theory. Configurations. Chern-Simons theories can be defined on any topological three-manifold M, with or without boundary. As these theories are Schwarz-type topological theories, no metric needs to be introduced on M. Chern-Simons theory is a gauge theory, which means that a classical configuration in the Chern-Simons theory on M with gauge group G is described by a principal G bundle on M. The connection of this bundle is characterized by a connection 1 form A, which is valued in the Lie algebra G of the Lie group G. In general, the connection A is only defined on individual coordinate patches, and the values of A on different patches are related by maps known as gauge transformations. These are characterized by the assertion that the covariant derivative, which is the sum of the exterior derivative operator D and the connection A, transforms in the adjoint representation of the gauge group G. The square of the covariant derivative with itself can be interpreted as a G-valued 2 form F called the curvature form or field strength. It also transforms in the adjoint representation. Dynamics. The action S of Chern-Simons theory is proportional to the integral of the Chern-Simons 3 form. The constant K is called the level of the theory. The classical physics of Chern-Simons theory is independent of the choice of level K. Classically, the system is characterized by its equations of motion, which are the extrema of the action with respect to variations of the field A. In terms of the field curvature, the field equation is explicitly the classical equations of motion are therefore satisfied if and only if the curvature vanishes everywhere, in which case the connection is said to be flat. Thus, the classical solutions to G. Chern-Simons theory are the flat connections of principal G bundles on M. Flat connections are determined entirely by holonomies around non-contractible cycles on the base M. More precisely, they are in one-to-one correspondence with equivalence classes of homomorphisms from the fundamental group of M to the gauge group G up to conjugation. If M has a boundary N, then there is additional data which describes a choice of trivialization of the principal G bundle on N. Such a choice characterizes a map from N to G. The dynamics of this map is described by the Wess-Zumino-Witten model on N at level K. Quantization. To canonically quantize Chern-Simons theory, one defines a state on each two-dimensional surface sigma in M. As in any quantum field theory, the states correspond to rays in a Hilbert space. There is no preferred notion of time in a Schwarz-type topological field theory, and so one can impose that sigma be Cauchy surfaces. In fact, a state can be defined on any surface. Sigma is codimension 1, and so one may cut M along sigma. After such a cutting, M will be a manifold with boundary, and in particular classically the dynamics of sigma will be described by a WZW model. Witten has shown that this correspondence holds even quantum mechanically. More precisely, he demonstrated that the Hilbert space of states is always finite-dimensional and can be canonically identified with the space of conformal blocks if the GWZW model at level K. Conformal blocks are locally holomorphic and anti-holomorphic factors whose products sum to the correlation functions of a two-dimensional conformal field theory. For example, when sigma is a two-sphere, this Hilbert space is one-dimensional and so there is only one state. When sigma is a two-torus, the states correspond to the integrable representations of the affine Lie algebra corresponding to G at level K. Characterizations of the conformal blocks at higher genera are not necessary for Witten's solution of Chern-Simons theory. Observables. Wilson loops. The observables of Chern-Simons theory are the endpoint correlation functions of gauge invariant operators. The most often studied class of gauge invariant operators are Wilson loops. A Wilson loop is the holonomy around a loop in M, traced in a given representation R of G. As we will be interested in products of Wilson loops, without loss of generality we may restrict our attention to irreducible representations R. More concretely, given an irreducible representation R and a loop K in M, one may define the Wilson loop by where A is the connection one form and we take the Cauchy principal value of the contour integral and is the path-ordered exponential. HOMFLY and Jones polynomials consider a link L in M, which is a collection of L disjoint loops. A particularly interesting observable is the L-point correlation function formed from the product of the Wilson loops around each disjoint loop, each traced in the fundamental representation of G. One may form a normalized correlation function by dividing this observable by the partition function Z, which is just the zero-point correlation function. In the special case in which M is the three-sphere, Witten has shown that these normalized correlation functions are proportional to known not polynomials. For example, in G equals U Chern-Simons theory at level K, the normalized correlation function is, up to a phase, equal to times the HOMFLY polynomial. In particular, when n equals 2, the HOMFLY polynomial reduces to the Jones polynomial. In the SO case, one finds a similar expression with the Kaufmann polynomial. The phase ambiguity reflects the fact that, as Witten has shown, the quantum correlation functions are not fully defined by the classical data. The linking number of a loop with itself enters into the calculation of the partition function. but this number is not invariant under small deformations and in particular is not a topological invariant. This number can be rendered well-defined if one chooses a framing for each loop, which is a choice of preferred non-zero normal vector at each point along which one deforms the loop to calculate its self-linking number. This procedure is an example of the point-splitting regularization procedure introduced by Paul Dirac and Rudolf Peierls to define apparently divergent quantities in quantum fields theory in 1934. So Michael Uttier has shown that there exists a canonical choice of framing, which is generally used in the literature today and leads to a well-defined linking number. With the canonical framing, the above phase is the exponential of 2 pi I times the linking number of L with itself. Relationships with other theories. Topological string theories in the context of string theory. A.U. Chern-Simons theory on an oriented Lagrangian 3-submanifold M of a 6-manifold X arises as the string field theory of open strings ending on the de-Bruno wrapping X in the A-model topological string theory on X. The B-model topological open string fields theory on the space-filling world volume of a stack of D5 Browness is a 6-dimensional variant of Chern-Simons theory known as holomorphic Chern-Simons theory. WZW and matrix models Chern-Simons theories are related to many other fields theories. For example, if one considers a Chern-Simons theory with gauge group G on a manifold with boundary, then all of the three-dimensional propagating degrees of freedom may be gauged away, leaving a two-dimensional conformal field theory known as AG-Wess-Zumino-Witten model on the boundary. In addition, the U and SO Chern-Simons theories at large N are well approximated by matrix models. Disambiguation needed. Chern-Simons, the Kodamar wave function and loop quantum gravity. Edward Witten argued that the Kodamar state in loop quantum gravity is unphysical due to an analogy to Chern-Simons state resulting in negative helicity and energy. Witten Chern-Simons gravity theory in 1982. Désir, Jackie and S. Templeton proposed the Chern-Simons gravity theory in 3 dimensions, in which the Einstein-Hilbert action in gravity theory is modified by adding the Chern-Simons term. Désir, Jackie and Templeton in 2003. Jackie and S. Y. Pi extended this theory to 4 dimensions. Jackie and Pi and Chern-Simons gravity theory has some considerable effects not only to fundamental physics but also condensed matter theory and astronomy. The 4-dimensional case is very analogous to the 3-dimensional case. In 3 dimensions, the gravitational Chern-Simons term as this variation gives the cotton tensor. Then, Chern-Simons modification of 3-dimensional gravity is made by adding the above cotton tensor to the field equation, which can be obtained as the vacuum solution by varying the Einstein-Hilbert action. See also dimensional topological gravity. Chern-Simons matter theories in 2013. Kenneth A. Intraligator and Nathan Seiberg solved these 3D Chern-Simons gauge theories and their phases using monopoles carrying extra degrees of freedom. The Witten index of the many vacua discovered was computed by compactifying the space by turning on mass parameters and then computing the index. In some vacua, supersymmetry was computed to be broken. These monopoles were related to condensed matter vortices. The n equals 6 Chern-Simons matter theory is the holographic dual of M theory on Chern-Simons terms in other theories. The Chern-Simons term can also be added to models which aren't topological quantum field theories. In 3D, this gives rise to a massive photon if this term is added to the action of Maxwell's theory of electrodynamics. This term can be induced by integrating over a massive charged Dirac field. It also appears, for example, in the quantum Hall effect. 10 and 11-dimensional generalizations of Chern-Simons terms appear in the actions of all 10 and 11-dimensional supergravity theories. one-loop renormalization of the level. If one adds matter to a Chern-Simons gauge theory, then in general it is no longer topological. However, if one adds n Majorana fermions, then, due to the parity anomaly, when integrated out, they lead to a pure Chern-Simons theory with a one-loop renormalization of the Chern-Simons level by -n2. In other words, the level K theory with n fermions is equivalent to the level K-n2 theory without fermions. Homomorphism. From the algebra of G, adjoint invariant polynomial on G to the cohomology. If the invariant polynomial is homogeneous, one can write down concretely any K form of the closed connection omega as some 2K form of the associated curvature form omega of omega. In 1974, Chern and J. H. Simons had concretely constructed a form df such that, where T is the Turnbull homomorphism, this form is called Chern-Simons form. If df is closed, one can integrate the above formula, where C is a dimensional cycle on M. This invariant is called Chern-Simons invariant, as pointed out in the introduction of the Chern-Simons paper. The Chern-Simons invariant CS is the boundary term that cannot be determined by any pure combinatorial formulation. It also can be defined as wet invariants and three-manifold invariants such as the Jones polynomial. Particularly, Chern-Simons theory is specified by a choice of simple Lie group G known as the gauge group of the theory, and also a number referred to as the level of the theory, which is a constant that multiplies the action. The action is gauge-dependent. However, the partition function of the quantum theory is well defined when the level is an integer and the gauge field strength vanishes on all boundaries of the three-dimensional spacetime. The classical theory. Mathematical origin. In the 1940s, Chern and A. Weil studied the global curvature properties of smooth manifolds M as the RHAM cohomology, which is an important step in the theory of characteristic classes in differential geometry. Given a flat G-principal bundle P on M, there exists a unique homomorphism, called Turnbull Homomorphism. The Chern-Simons theory, named after Shen Chern and James Simons, is a three-dimensional topological quantum field theory of Schwartz type, developed by Edward Witten. It is so named because its action is proportional to the integral of the Chern-Simons 3 form. In condensed matter physics, Chern-Simons theory describes the topological order in fractional quantum Hall effect states. In mathematics, it has been used to calculate